Okay, so today we are going to be starting a new topic, scattering theory. Okay, so as I told you at the beginning of the course, there is roughly three big topics that we will cover this semester. The first was angular momentum, the second was time-dependent perturbation theory, and then finally scattering. So the rough plan is to spend some time on scattering, set up the scattering problem, the quantum mechanical problem, and then look at a couple of examples. And then if we have time remaining, and I suspect we will have time remaining, we will revisit some of the topics that were left out and try to do a little more justice to some of the topics. Okay, so that is the rough plan for the rest of the semester. Okay, so let's begin. Scattering theory. So before we begin, have all of you done scattering in your classical mechanics course last semester?
Yes, sir.
So we will begin by revising some of the things that you already know. I will not spend too much time on this because I'm sure you have seen this in detail before. And for those of you who have not seen it, I'll be brief, but it'll be self-contained. And don't worry, you are not missing anything if you've not seen this in detail before. You can always take up any textbook on quantum mechanics and go through the initial discussion on scattering, and it will cover mostly what I will just talk about. Okay, let's go. So let us begin by understanding what is the scattering problem, right? So scattering problem is actually quite easy to state, but the setup is quite elaborate, so we have to go through it in some detail. But roughly speaking, this is what we do. So we have what is called some amount of target, okay? So the target is what is causing a potential. So for example, this could be some charge, right? Some amount of positive charge that is setting up some kind of a Coulomb field around it. And in this, we throw a particle, or in general, a bunch of particles, okay? And then we understand how these particles behave in this force field. In general, we are not looking at an attractive potential, we are looking at repulsive potentials, right? So I will redraw this figure slightly better. So we define what is called as a scattering center. So let me denote this by this small red circle here, okay? This is what I will call as a scattering center, and there is nothing mysterious about this term. This is where I place my target, and this is setting up a potential around it, a force field around it, a repulsive force field around it. And I'm throwing some particle in this force field. So how is the particle going to behave? Well, if it's an attractive potential, it will try to form a bound state, right? But if it's a repulsive potential, it wants nothing to do with this target, so it wants to get away from the target as soon as possible. So let us actually draw a line, straight line through this scattering center, not like that. Okay. Now I'm going to be throwing a particle, let us say from here. Okay, excuse me. So what's it going to do? It's going to keep going along a straight line. I'm going to throw it with some kinetic energy. So I'm talking about a classical picture to start with, and then we will move on to quantum mechanics. Okay, so it's going to keep moving, but at some point it's going to start feeling this force due to this, feeling the potential due to this particle or target or whatever it is. And since it is a repulsive potential, it's going to be deflected and start moving away from the scattering center. It's going to be scattered away, okay? So usually it is you who's throwing this object in this potential field, and you can either throw it along the scattering center or in general at some height away from the scattering center. And this height that you throw it from, we'll call this B, and this is called the impact parameter, okay? So the impact parameter, of course, is a crucial, why is the impact parameter important? Because if my impact parameter is very, very large, then if I throw it from this point, let us say, then the potentials that you typically consider are potentials that die down after a certain point. In other words, the potential set up by this target, so this guy here, that is setting up the potential, source of the potential or force equivalently, it doesn't matter, right? So let's call this potential instead of force because we are looking at potential scattering. Okay. So the potential is such that V of R goes to 0 as R goes to a very large number. Okay. So I do want a non-zero potential, but I do want it only in some amount of space. I don't want the potential to extend all the way to infinity. Now you might argue, for example, that Coulomb potential is 1 over R. It's never really equal to 0. But for all practical purposes, beyond a certain measure of distance, the 1 over R potential falls to 0, right? So effectively, the particle feels no force. So it is only for a short distance the particle is traveling in the potential. So what I can typically do when I set up the scattering problem is make use of this physical fact, and that is why this impact parameter is important even in classical scattering, because I cannot throw the particle at a very large height from the scattering center or the target, okay, because the particle will feel no force. So there is some amount, so there is some relationship, as you can easily guess, between B, the impact parameter, and the scattering angle. So what is a scattering angle? The scattering angle is defined as follows. So if the target were not there, this guy would have continued traveling along a straight line like this, right? But since there is a target, since there is a non-zero potential, it has been scattered off in this direction. So this angle between the scattering direction and the initial direction is called theta, and theta is called the scattering angle. Okay. So the goal of classical scattering is to figure out what the scattering angle is. Okay. So classical scattering involves solving the classical equations of motion to determine the scattering angle theta as a function of B and the energy of the particle. Okay, so this particle is coming in with some energy E, kinetic energy E. Okay. So this is what we have probably done last semester, but we will actually refine this picture a little more. Okay. By the way, if you have any questions at any point, please stop me and ask. Okay. So our goal is to determine the scattering angle. At least we are now clear on what it is that we want to compute, but we will keep understanding what is it that we want to compute in some more detail. So in general, for example, you don't just throw one particle, right? So you throw a bunch of particles. Now, for example, in colliders that are built around the world to do particle physics experiments, there is two kinds of collisions that can possibly happen. There are what are called fixed target experiments. Fixed target experiments are essentially what we have just discussed here. So you place a target that is an immovable target at some point, okay, and then you throw a bunch of stuff at it. Now, this is actually a very, very good source of information in high energy physics, because as you bombard particles at very large energies, you can understand a lot about the elementary constituents of matter. And if there is any new stuff that is to be discovered, any new particle that is to be discovered, they can be produced as a result of all these collisions and scatterings. Okay. So this is what is called in the parlance, scientific parlance, a fixed target experiment. Okay. On the other hand, you also have colliders like the Large Hadron Collider. A Large Hadron Collider is basically a circular collider in which you collide bunches of protons, right? So in that case, there is not a fixed target. There is two bunches of protons moving in opposite directions and colliding with each other. Okay. Now you can, of course, use the same formalism by going into the rest frame of one of the protons, in which case there is only relative motion. The mathematics would work out the exact same way, but typically, from an experimental point of view, there are actually two different types of collisions one can envisage: fixed target experiments and experiments in which both bunches of beams are moving towards each other. Okay. So what we will do is basically use this picture that we have, fixed target experiments. All right. So what happens if I throw a bunch of particles? So if I throw a bunch of particles at this target, of course, I will always assume that I'm throwing a uniform bunch of particles. In other words, the number density doesn't fluctuate rapidly between point to point in space, and all of these particles have the same kinetic energy E. That is always easy to adjust, at least from the classical perspective, it is easy to adjust because I'll simply accelerate all the particles. If these are charged particles, I'll accelerate them through some kind of a linear accelerator to a common kinetic energy E. Okay, and then I will send this beam to meet a fixed target. So this is easy to think about, at least. So when I have a bunch of particles, I can set up the same problem, but I will have to use a slightly different language to set it up. So I can still talk about impact parameters. I can still talk about B and the scattering angle, but I will have to account for the fact that there is a whole bunch of particles. So what I will do is this: I will go and stand behind this target and look at the incoming beam head on, okay? And assume that there is a tube of particles. So there is with a volume of a tube or whatever it is. But whatever I do, when I look at it head on, I can always concentrate my attention on some circular cross section. So I will look at a particular circular cross section. It doesn't matter what the circular cross section is, but I will look, when I look head on at the incoming beam, I will look at some circular cross section. So I will draw a circle. Okay. In fact, I will, sorry, I don't think this is showing up, so I will have to reshare again. Okay. In fact, I will not even look at the whole. So this circular cross section has a whole bunch of particles, but I will not even look at all the particles inside this ring. What I will do is basically I will consider an annular ring. So I will consider a small circle, excuse me, on top of this circle. Okay. And only consider the particles that is in between these two circles. So I'm looking at the beam head on, and I'm concentrating my attention on some kind of an annular ring. Okay, so basically there's particles everywhere, but I'm concentrating my attention on the particles in this ring, okay, between these two rings. Okay, so let us say that this is the scattering center. So this is the center. Excuse me. So this is at an impact parameter B, okay, and this height is an impact parameter B plus dB, okay. Now I'll actually make it even more simple by not considering all the particles in this annular ring, but I will simply look at a small portion of it. Okay, so let us call a small portion. Of it. Okay, now let's call this area d sigma. Okay, so what is it that we are doing? Since we assume that the entire beam is composed of the same kinds of particles with same energy, I can concentrate my attention on a small bunch of particles. And in order to make my geometry easier, I'm considering a small bunch of particles that is in the space between two rings with impact parameters b and b plus db. My goal, so if you want to look at, imagine this picture, please imagine this picture as being drawn head on from the target. So the target is somewhere here. Okay. So this is the target. So you're standing right here and then looking at this beam head on. Now, what will you see? The question is, what will you see? Well, so every single particle is going to follow a trajectory like the one that I draw before, right? It's going to come, and then when it starts feeling this repulsive potential, it's going to be scattered away. So every particle on the surface of this ring is going to come, okay? It's going to travel like this. And then at some point, they're going to be scattered in this direction. Similarly, every particle on top of this is going to come like this, and then they're also going to be scattered at some angle, so on and so forth. Okay, so every particle or this area d sigma on this ring is now going to be scattered away, and it's going to be, excuse me, it's going to look something like this. Okay, so basically it's easy for you to see, even though my picture might not be very accurate. All of these particles are going to be scattered, and this area d sigma is going to be scattered away to, like, so if I imagine this picture, if I simply extend this, excuse me, extend this, right? It's easy for you to see that this is going to be, if you imagine two lines like this, then this annular ring on the right hand side is going to be the tip of a cone. Okay, so that all these particles within this initial d sigma are now going to lie in some solid angle d omega at the tip of this cone. Does this make sense? Any questions or any comments? So there is a solid angle, so I'll finish. Because I'm using the same color, I'll use the same red. And let me call the solid angle that this area subtends as some d omega. Okay, so the effect of scattering can be quantified by looking at this particular picture, where I consider a small area d sigma. Okay, now that has been scattered off, and this area d sigma is now lying in within a solid angle of d omega subtended by a cone. Okay, so my job now is to understand how exactly this area d sigma is lying inside this solid angle d omega. So that is the problem of classical scattering for a bunch of particles. So let us actually set this up in terms of equations. So what is d sigma? Since I have taken a very simple geometry of a circle, d sigma is actually easy to understand. So let us call this the z-axis, excuse me. Z-axis, okay, and this angle around this is some phi, okay, the azimuthal angle. Now d sigma, of course, would be equal to b db d phi. Okay, so this is the area of this infinitesimal annular ring. Okay, if you don't believe me, you can simply try integrating this. How will you integrate this? You integrate this by integrating over b, which moves you up and down, and you integrate this over phi, which moves in a circle. So if you integrate this b db d phi, you should get the area of the entire circle. So integral d sigma would be integral b db from some 0 to b, and d phi from 0 to 2 pi. And if you do this integration, you will get pi b square, which is the area of a circle of radius b. Okay, so d sigma, which is b db d phi, can be thought of as the infinitesimal area that is lying in this annular ring. Okay. So how about d omega? Well, d omega you know, is sine theta d phi. Now here's an approximation that I will make. Now, obviously, there is going to be what is theta? Theta is already defined, right? So I will actually make I'll define what theta is in this picture also. So if you call this the scattered direction, right? So this is theta. Okay. Now the angle made by the top portion is theta plus delta theta. Since these are very close to each other, it's going to be scattered off by a very, very slightly larger angle, theta plus delta theta, because it is at a slightly higher impact parameter than the lower part of the ring. Okay? So d omega is sine theta d phi. Now, why is the ring growing? The ring is growing because there is non-zero scattering, so there is a non-zero theta involved. But if you look at these two equations, I've taken this azimuthal angle subtended by this d omega to be the same d phi as the original d phi. If the potential were not azimuthal symmetric, okay, if there is no azimuthal symmetry in the potential, then this d phi would be different from this d phi. Okay, but I'm going to be using those examples of potentials which have azimuthal symmetry, in other words, which are rotationally symmetric or central potentials. So in other words, I'm going to choose V of R to be V of mod R. Okay. In other words, what I'm basically claiming is that even though there is a non-zero theta dependence, there is no non-zero phi dependence. In other words, this ring is not tilted with respect to the z-axis. Okay. So the angle subtended is the same phi. Okay. So with this assumption, we can go ahead and try to set up this problem, the classical problem. And we can actually see that the same definition carries through in quantum mechanics also. Okay. So basically the question is, what is the relation between this d sigma and this d omega? To understand this, we simply divide these two equations. So d sigma by d omega is basically b over sine theta dB d theta. Now, why a modulus? Well, modulus because I'm only interested in understanding how the exact dependence on b on theta is. Okay, so whether I'm looking at the top portion of this axis, the bottom portion of this axis doesn't really matter. So I'm only interested in the modulus. In fact, the left-hand side should also be a modulus, but usually in most textbooks we suppress the left-hand side modulus. But you should understand this as the modulus being on both sides. So this quantity d sigma over d omega is of fundamental importance, and this is called the differential cross section. So this is called the differential cross section. Okay. And this carries a lot of information. For example, it tells you what is d sigma over d omega. It tells you a relation between the initial flux of particles that are there in a small portion d sigma to the final flux of particles that are there on a cone subtended by an angle d omega. Okay. So this differential cross section in a physical sense can be also understood as the scattered flux density over the initial flux density. Of course, if I integrate this d sigma over all possible solid angles d omega, I get what is called the total cross section. Sigma equals d sigma over d omega times d omega. Okay. So what is the total cross section? The total cross section in some sense is the area of the incoming beam that is actually being scattered. Okay, so the differential cross section carries more information than the total cross section, but the total cross section is roughly speaking the amount of the total area of the beam that is actually being scattered. What does it really mean? Well, for example, there can be particles that are at a very, very large impact parameter, right? So if these are at a very large impact parameter, they are sufficiently far away from the scattering center, so they don't feel any potential. So among this incoming bunch, there is only a There's only a portion of bunch that actually feels the force from the target. And that is the bunch that is being scattered. So the scattering cross-section measures the area, the cross-sectional area of the bunch of incoming particles that are actually being scattered. Okay. The differential cross-section is a measure of the amount of particles that are scattered away in some solid angle d omega to the amount of particles that are incident on some small area d sigma. Okay. So this is the physical picture behind the classical scattering theory. So the classical scattering theory, yes.
So why did you say that differential cross-section holds more information than the total one?
The differential cross-section holds more information because in the total cross-section, you integrate over all the angles. Right? So when you integrate over all the angles, you lose information, detailed information about the how a particular small bunch of particles is being scattered off by this potential. Okay. So in other words, differential cross-section means I can zoom in microscopically and look at a small bunch of particles and individually track this bunch of particles to see where they finally end up with. Okay. But in total cross-section, that information is lost. Total cross-section is simply a measure of the total area of the beam that is scattered. So I cannot track individual particles and predict where they land.
Okay, sir.
Okay. So it doesn't mean that it is not important. Of course, that is also a very important measure. But the differential cross-section contains angular information.
Yes, sir.
So typically, what is this d omega? So I should also mention this. Of course.
Sir.
Yes.
Sir, in the d sigma integral, sir, it should be 2 pi b db. So the limit should be b to b plus db, right? It is not. It is an annular ring. Hello.
Sorry.
Sir, the total area of the annular ring, which would be integral of d sigma that you have written, that should be from the limit should be from b to b plus db. So that we'll get 2 pi b into db. That would be the area of the annular ring. No?
Sure, but I can also integrate over the entire circle, right? So it is true that I can also integrate over this entire annular ring. I will get obviously 2 pi b db because it is the circumference times the thickness. That is the area of the angle. So this is what you're saying. So I should not do this. But if you integrate d sigma, you should get, so, excuse me. The phi integration is of course just 2 pi, right? And then this is just b db, and I can understand this as 2 pi b is the circumference of this circle and b is the thickness. So this is the area of cross section of this annular ring. That's what you're saying, right?
Yes.
Yes, that is true. But I can also integrate over the entire circle by going from 0 to the entire b. So instead of assuming that this d sigma is only covering this annular ring, I can also assume that the d sigma is covering the entire ring, entire circle. Okay. So whatever it is, this d sigma b db d phi is the area subtended by an angle d phi on an annular portion of thickness db. Okay. So this was just a way to justify this formula. If you already know this formula to be true, there's no need to worry about it. So do you agree with this formula? That is all the question.
Yes, sir.
Okay. Any other questions or comments? So you have seen all of this before in your classical scattering theory?
Yes, sir.
Okay, all right. So just to drive home the point, we will actually quickly look at one example, which I will not work out, but to reinforce the physical aspect of what cross-section is. A very common example that is given is what is called hard sphere scattering, right, in classical mechanics. What is hard sphere scattering? Well, instead of worrying about all these targets and things like that, just put a ball there. So if I imagine that the target is actually a spherical ball of radius some capital R. Okay. Now I'm shooting, instead of a bunch of particles, let me shoot very, very small marbles or whatever, small particles. Okay. So if this is my scattering center. Okay. So let me shoot it from some distance b. Okay, and then this, sorry. And this guy is of course going to be deflected hard in this direction. Okay, so if you extend this and call this angle alpha, okay, and this of course is a scattering angle because this is the incident direction and this is a scattered direction. So this is a scattering angle. This is my impact parameter B. Okay. Now, if you call this alpha, you can, of course, this is the opposite angle alpha, and you can use simple geometry to argue that this is also equal to alpha, in which case there is a relation, and this radius of this ball is some capital R. So B is R sine alpha, okay? And since theta plus 2 alpha is pi, you can actually claim that alpha is basically, what is this? Theta plus 2 alpha is pi. Right? So 1/2 pi minus theta. So using this simple geometry, you can actually claim, you can easily see that B in this case is R cosine theta over 2, which means dB is basically minus R over 2 sine theta over 2. Right? So in this case, the relation between d sigma and d omega is actually very easy to determine. D sigma over d omega is basically B over sine theta mod dB over d theta, which in this case becomes R cosine theta over 2 divided by sine theta, and dB d theta, there is a d theta here, is of course R over 2 sine theta over 2. So put everything together and you actually get d sigma over d omega in this case is just R square over 4. Okay. Now, this is actually a very trivial example where the scattering differential cross section has nothing to do with the scattering angle. In general, it is a function of the scattering angle, but in this case, it is not a function of the scattering angle. But if you actually integrate this d sigma d omega, you get the total cross section. What is the total cross section? This is basically d sigma d omega times d omega. In this case, d sigma d omega is a constant, and the integration of d omega is just going to give you 4 pi. So this is basically pi r square. So what is, how do you interpret this sigma then? This is basically the geometric cross section of this sphere of radius r. So what does this actually mean? It means that the area of the particles that are actually going to be scattered is pi r square, which means if I draw a circular cross section of particles that are actually approaching, then the area of the particles that is actually going to be scattered is basically going to lie in pi r square. Now, this is obvious in this case because if the particles are incident with an impact parameter B that is more than capital R, of course, they're just going to go straight up, right? They're not going to hit the sphere and they're not going to be deflected. So in this case, it is actually very easy to see why this concept of cross section is important. In this case, it is actually very clear that the area of the particles that are going to be scattered lie on a circle whose radius is pi r square, where r is the radius of the ball that is actually doing the scattering. Okay. It is harder to see for more complicated potentials, but the physical picture is still the same. Okay. So this is why this hard sphere scattering is often used as an example in classical mechanical scattering. Another very important example historically is the Rutherford scattering. Now, I don't have to tell you guys Rutherford's experiment where he basically understood the structure of the atom. So Rutherford scattering is basically the potential V of R is 1 over R potential, right? With A greater than 0, that is important, right? Because we are looking at a repulsive potential, not an attractive potential. And if you work out d sigma over d omega for this potential, you would actually get a very important formula. A over 4E quantity square divided by 1 over sine to the 4th theta over 2. Okay. So contrast this with the previous expression where d sigma over d omega was just a constant r square over 4. So this is why I was saying that in general, d sigma over d omega is some complicated function of the energies of the incoming beam and the scattering angle. Okay, so E is the energy, kinetic energy of the incoming beam, and theta is a scattering angle. Okay, now Rutherford did all his experiments much before the advent of quantum mechanics. Right? So quantum mechanics only came into being, at least in the form of Schrodinger's equations and things like that. It came to being in the 1920s. Right? This was done way before. So Rutherford, when he wanted to understand his scattering experiments, to compare experiment to theory, he only had the classical scattering theory to compare with. And surprisingly enough, his experiments agreed very well with the classical result. So this is the classical result. Okay, so Rutherford's experiments agreed very well with the classical result. So there is two ways to interpret this. This might be a little surprising because an atom is a quantum mechanical object. So the formula should be a quantum mechanical version of the classical d sigma over d omega. So either quantum mechanics is not important, or quantum mechanics gives no correction to the Rutherford scattering. Okay, so there is two possible conclusions. If Rutherford's experiments agreed well with classical formula for scattering, there is two conclusions: quantum mechanics is not relevant, or two, in this particular example, quantum mechanics does not give any corrections to Rutherford scattering. So obviously the first option is incorrect. Quantum mechanics is very important in the atomic realm. But it turns out that in the case of Rutherford scattering, very surprisingly and counterintuitively, quantum mechanical formula for the differential cross-section is exactly the same as the classical formula. We will talk more about this when we set up the quantum mechanical picture. But have you derived this in your classical mechanics lectures?
Not the Rutherford scattering.
Oh, you have not done this, Rutherford scattering?
No, sir.
Okay, so in that case, then I will push this to a tutorial because it is very important for you to understand the classical calculation also. Okay. Anyway, so that is about the setting up of the problem in classical mechanics. And classical mechanics, basically what we are looking for is a formula for the differential cross section. So again, I will again tell you that this total cross section can be understood. Oh, I have to reshare again. Sorry about that. Okay. So the total cross section can be understood the area of actually total area of the incoming beam that is scattered by the potential, and the differential cross section can be understood as the ratio of the scattered flux density divided by the initial flux density, or more correctly, the density of the particles that is being scattered in some solid angle d omega divided by the initial density of the particles that are lying in some small area d sigma. Okay, so this is the classical notion of scattering. So I will simply set up the quantum mechanical picture, and then we will stop and we will continue this discussion in the next class. So I'll basically introduce what is called the scattering amplitude. So quantum mechanical picture of scattering. So at the outset, let me say that if you want to do a good analysis, a thorough analysis of quantum mechanical picture of scattering, what should you do? Well, you cannot take one particle, right? So you cannot take a wave function for a free particle, because So you can differentiate between two regions. The first region is where the particle does not feel the potential at all, at the far in minus infinity, right? This is what we did in the one-dimensional scattering problem. Now there is some non-zero potential at some in some region of space, and then far enough away from this potential, the particle is again free, right? So you have a free particle initially, which comes in contact with a force field for a very short interval of time, and it is being scattered. And after it is scattered, asymptotically, you get again another free particle. Okay? So this is what we used in one-dimensional scattering in the last semester briefly. But of course, the actual picture of scattering is slightly more involved. So in the one-dimensional scattering picture, 1D picture, right? Remember that we argued that, for example, you have a particle that is coming in, and there is some region where V is not equal to 0, and then V equal to 0 here, V equal to 0 here, right? So, and then it is going off. So there is an incoming wave, and there is an outgoing wave. Okay. Now we also accounted for the fact that there is the part of this beam can be reflected. So this is the x is equal to 0, let us say, right? At x is equal to minus infinity, we argued that the form of the wave function should be something like e to the ikx plus b e to the minus ikx. And at x is equal to plus infinity, we argued that it should be c e to the ikx. Okay, it should be the same k because of momentum energy conservation, right? So we also argued that look, e to the ikx is not a normalizable wave function. So strictly speaking, I cannot use this particular form to understand scattering. The way I should actually understand even this one-dimensional picture of scattering is I should first form a wave packet, right? A wave. So remember our description of free particle. You actually form a wave packet that is peaked at some very central value of momentum, some k0 or something like that, so that the incoming beam has a definite momentum and can be thought of as a free particle in the strict quantum mechanical sense. And you scatter this off, and then you look at the final wave packet that is emerging from the other side. Okay, and then you calculate the R and T, the reflection and transmission coefficients in this picture. And surprisingly enough, you get the exact same value had you started with this particular very simple notion of e to the ikx plus e to the minus ikx. So you basically claim that even though I should do it more correctly in the form of wave packet scattering, I will simply use the e to the ikx and e to the minus ikx language because it is much simpler to work. So this is what we did in the one-dimensional scattering problem. So what is it that we have to do in this case in proper three-dimensional quantum mechanical scattering? Well, strictly speaking, what we are going to do is we are looking at the solution of the Schrodinger equation, right? So we assume that there is a non-zero region. So there is a region in which there is a non-zero potential. So we can write down the Schrodinger equation for a particle moving in such a potential. Del square plus V of R psi of R equals E psi of R. Okay, I've assumed central potentials. V of R is just V of the distance. Okay, these are rotationally symmetric potentials. In other words, the scattering angle has just one angle theta and has no non-trivial dependence on the azimuthal angle phi. Okay, so this is something I'll assume from the get-go because it makes my picture easier, and most of the potentials that we work with are indeed rotationally symmetric. Okay, so then we will use the same picture as above. We will send an incident wave, okay, a plane wave with some energy E, and I will call the direction in which the particle is traveling the initial Z direction. So the incident wave psi incident of R is nothing but e to the I k z. Okay, so again we can do this with wave packets, but our results are quantitatively the same, so we will use this simple non-normalizable wave functions. Of course, the energy of this particle is h bar square k square over 2m, where m is the mass of the particle that is being thrown in this potential. Now, what happens after scattering? After scattering, the wave spreads out, okay, as a spherical wave. Of course, a spherical wave, I remind you, is of the form e to the ikr over r. Have you seen spherical waves in electromagnetism course? You know what plane waves are, of course. Do you know what spherical waves are? What's the formula for a spherical wave? Okay, so if you don't, a spherical wave is of the form e to the ikr over r. Okay. So the scattered wave, the ansatz in quantum mechanics is that a scattered wave at distances very, very large compared to the scattering center is basically a spherical wave with some so the wave basically spreads out as a spherical wave, except that the amplitude of this the phase of this spherical wave and amplitude can vary around the sphere. Okay. Now for central potentials, psi scattered of r is only a function of theta and not a function of phi. Okay, so this is basically just f of theta times e to the ikr over r. Now we will stop at this point and we will pick this up later, but the central job of quantum mechanical scattering is to find out what this f of theta is. Now you might actually disagree with this, claiming that look, you have already you should actually solve the Schrodinger equation and find out what the scattered wave is, right? So strictly speaking, if I can do that, I will do it. But in general, problems are hard, right? So it's not easy for you to figure out what this exact solution of Schrodinger's equation is. Okay, so what we basically do is claim that at large enough distances from the scattering angle. Why do we care about large enough distances from the scattering center? Because this is something I was saying, but did not complete my thought. Because see, this d omega, this solid angle subtended by this bunch of particles, it is, where do you actually put this ring? So typically what experimentalists do is they send in a bunch of beam, put a target particle, and then look at the angular distribution of particles that is coming out. So in other words, you have a detector of particles that is recording all the particles coming out. So a very, very trivial model of this is basically just put a big pile of sand. Okay, and then you shoot particles and all these particles get stuck in the sand. And then you look at the distribution of particles that is being stuck in the sand. So this sand, this whole barrel of sand that is absorbing all these particles is a very primitive example of what is called a detector. Okay, so this is a detector. A detector detects the particles that are being scattered off by some potentials, not necessarily central potential. So usually this detector is placed far enough away from the target so that our approximation is always valid, that the region at which you are interested in understanding where the particles are scattered, this region is far enough away from the target placement that you are looking at basically asymptotic solutions. So this is an asymptotic solution. So this looking at regions very, very large compared to the region where this scattering is actually taking place. Okay, so in these regions, basically the particle is a free particle, so I don't have to worry about all these potentials anymore. So once the particle is scattered off, it is going to propagate as a spherical wave, and all I have to basically figure out is what is the amplitude of the spherical wave. So this f of theta in quantum mechanics is called the scattering amplitude. And this is of fundamental importance in quantum mechanical scattering, because f of theta is basically related to the differential cross section that we discussed before in our discussion on classical scattering. So we will take this up in the next lecture and show that indeed d sigma or d omega, using this definition that differential cross section is basically scattered flux density divided by the initial flux density. Using this, will actually show that modulus f of theta squared is basically the differential cross section. So in the quantum mechanical picture of scattering, with the ansatz that the scattered wave, asymptotic form of the scattered wave, is basically a spherical wave with some amplitude that depends on the polar angle theta. The job of calculating the differential cross section basically boils down to the job of calculating the scattering amplitude. Okay, so the quantum mechanical picture of scattering is basically a setup to calculate this scattering amplitude. So how we actually calculate the scattering amplitude, we'll actually do it methodically in the upcoming lectures. So I will stop at this point, and if you have any questions,